Hello, it's Keith here, and this is lesson 2 of the platform-specific series of my PDP-11 UKNC programming tutorials. We're looking at PDP-11, the old server programming language again, but we're going to be programming a Russian machine known as the UKNC, which was an educational computer, very much like a Commodore 64 or Spectrum. They used the server processor and they converted it into a desktop computer, and the desktop computer is actually in most cases PDP-11 compatible. In the terminal works the same way, it has a terminal emulator. We'll actually be using that terminal to configure some of the screen settings today. But the beauty of the UKNC is it can do graphics, and so we can have this rather nice Chibico bitmap here. This is a 4-color bitmap today. The system itself can do 8 colors, that's 3-bit planes, but only 2 of them are directly accessible from the main CPU that runs the program. The other one and the 3-color access mode is accessible from the peripheral processor, the sub CPU, and we'll be looking at that at a later date. But that's a little bit trickier, and this is the simplest example today. So what we do to achieve today's example is first we set the screen up with some terminal commands. We send some bytes to the screen hardware, and that will configure the screen, clear the screen for us and things like that. And then we will transfer the bitmap data via some I/O ports that allow us to write straight to VRAM, and that allows us to write to 2 of the bit planes, which in the default colors gives us access to the green and red channels. The blue channel we don't have control of, and you will see that because where we got the terminal to write hello world, well, our Chibico overlapped that and we replaced the green and the red, but you can see the blue where the white hello world was has now become a blue hello world, and that's because the Chibico bitmap has left that bit plane totally unaffected. Now you can see this example is a little bit squashed up. That's just the screen mode. This is the 320 by about 240 I think it is screen mode, but we can change that if we just change a setting here. I'll show you this in a second, but if we just run again now we're in the 80 character wide mode, and there our Chibico is much more square. So we've got 2 options that we can use very easily, we're just with the same example. Now we are going to very briefly discuss the video memory and how it works. It's a little bit tricky. To be honest with you, I've only really finally I think got my head around it this week. I understood how to use this example before, but I didn't quite understand what was going on in the background. Now my understanding is that the UKNC has 3 banks of 64 kilobytes of memory. That's 192 kilobytes in total. The top half of each of these bytes, the top 32 kilobytes, is by default used for VRAM for the screen, and these are the 3-bit planes. And so the way I'm referring to them is that there's a blue bank, a green bank, and a red bank. All of the colors are reconfigurable, so that's it's a bit of a simplification, but I think it's a nice easy way of thinking things through in the default setting. So the top half of each of these is the VRAM. The bottom half of these is used by the system for the normal memory that runs our programs and our variables and all that kind of thing. And so the main CPU can access the bottom 32 kilobytes of banks 1 and 2, the green and red banks, but it can't access the blue bank at all. It can't access the RAM at all. The second processor is using the bottom 32 kilobytes of the blue bank, bank 0, for its RAM, and the rest of its accessible memory is actually ROM. Now the bottom 2 32 kilobyte banks are effectively using alternate bytes of the 64 kilobytes of accessible memory, and so the green bank is actually accessible from the even addresses, and the red bank is accessible from the odd addresses of the main CPU's memory, but only the bottom half of the actual physical banks of memory. So the logical 64K address space of the main CPU is the first 32K of the banks 1 and 2, and the second 32K is the VRAM by default. So basically this area is entirely used by our CPUs but isn't used at all by the VRAM by default, and this area here is entirely used by the VRAM and is totally inaccessible by either of our CPUs by default. Now we're only using the main CPU today, so the blue bank is totally out of our access. Now the way we access the memory, and we can actually access all of the memory from the CPU in this way, is we use something known as the wrap device. Now The wrap device is what I'm calling it. This is the documentation I've got on this is actually Russian documentation. I can't read Russian, so I've had to run it through Google Translate, and it's calling this device the wrap device. So I'm assuming maybe this means RAM access peripheral or RAM access support or something, but it could mean really annoying pigeon for all I know. It's coming up as wrap, so we're going to call it that because it sounds quite nice. So there's this device, this third device that accesses the memory, and this device accesses all the memory. It has 3 accessible ports to the main CPU, that's the one running our program. One is a RAM address port and the other 2 are data write ports, and this allows us to write to any memory position within the within bank 1 or bank 2. The full 128K can be accessed from the main CPU. The sub CPU, which we aren't using today, that's the peripheral CPU, can access even more. It can access all 3 banks and the entire range. So it has 1 address select port and 3 write ports for the 3 banks of memory. And that's why the sub CPU can write to any of the color channels within video RAM, and it can actually write to any RAM address on the system, including writing to the RAM that's being used by the main CPU. So anyway, a little bit tricky. Now, you're not going to really need to understand that today, but it's taken me so long to get my head around it. I didn't feel I'd be being fair to not mention it. I thought we'd better go into it and try and explain it at this point. But what we're going to do today is we're going to be selecting a VRAM address with port 176640, that's in octal, and then we're going to write a byte to 176642 and 6643 to write the green and red channels, and that will put our Chibico bitmap onto the screen. And all we need to do is calculate the correct RAM offset to select with port 176640, and that will select the location on the screen that our Chibico appears. Okay, well, after that rather complicated description out the way, let's go over to our source code and let's take a look at what we've got. Now, we can actually do everything entirely in hardware from the sub processor, the peripheral processor, but we're not going to use that today. So what we're going to actually do is we're going to use some terminal commands to set our screen up for us. So we're going to need some commands to write data to the screen, and we're going to use the ones that we learned before in the simple series, I think it was, where we learned how to get terminal commands, get commands and text straight to the screen. And so we've got a print character routine here, and this will check if the port is ready to receive data, and once it is, it will write a byte to this port here. 177566 is the port to send data, and 177564 is the port we need to test before we send the data. So that prints a character to the screen, and in my tutorials I use character 55 termination, so we've got a print string routine to use that termination, and we're using that print string routine to show a hello world message. It's a simple hello world. We can see it. Where is it? There it is, just a hello world there, character 255 terminated. This power symbol and this D, this marks that this is a decimal value, because by default it would be octal. So we're specifying decimal there, and that's our hello world message. And then here we've got a preparation routine here, which is an initialization, and we're using escape codes here. Escape codes are character 27, that's 33 in octal, and that's this here, and then the bytes that follow need to be configured for the screen. And so what we're doing here is we are selecting a screen mode. We can use 61 for 80 by 24 or 62 for 40 by 24. We can select either screen mode there. We're then setting up the colors. We're setting the foreground color to white and the background color of the font to black. We're then setting the screen color. We're setting the screen color to black here, and then we're clearing the screen. We can change these though. If we change this to a 1 and this to a 6 and we run again, well, now our hello world is in blue and yellow, so we've reconfigured the colors there. We can do that if we require. So that's how we can change our font and how we can set up our screen here. This is the easiest way. As I say, there's other ways that we can do things more directly, but we need to program the sub CPU for that. So that is actually harder to do. Now we need a bitmap for today's example. We've got one here, and this is in hexadecimal, so we're changing the radix to 16 here. If you want to create a valid bitmap, you can do so in my free AccuSprite editor. It's included in the downloads, and if you go to the PDP-11 menu here, you've got save raw bitmap options, and you can save a bitmap in the 2-plane format that you will need for today's example, and you just need to convert it and import it in here. So that's what we've done here. This is how I created the data for today's example. So we've got our bitmap there, and all we need to do is calculate the VRAM address for the destination that we want to show it. So I've got this get screen routine here, which will calculate the VRAM address from an X and Y coordinate. Now our screen base is at 1 and 5 zeros here in octal. So that's the start of the screen video memory, and each line is 80 units wide in decimal. It's 80 characters wide. So we're effectively multiplying the Y line by 80 here, adding the X line and adding the screen base here. And this is effectively setting R1 to the memory address that we want to show the Chibico bitmap to. So what we do next is we load the address of the Chibico bitmap into R0, the height in lines into R5, the width in bytes into R2, and this is actually in pairs of bytes because there's 2-bit planes, so we're moving 2 bytes at a time here. And then we select the VRAM address using that wrap device. We write the VRAM address we want to select to 176640 here, and then we write the pairs of bytes, the 2-bit planes, we're writing 2 bytes at a time, to 176442 here, and also to 176443, but we're doing that by default by the fact that we're writing 2 bytes at a time. So we're reading 2 bytes from our source, writing to the destination. We're increasing the destination after each write, because each of the addresses here has a different byte for the 2 banks at 176442 and 176443. So that's why we're doing 1 inc here, but we're writing 2 bytes here. We then repeat for the rest of the line, the other 6 bytes in the line. We then move down 1 line by setting R1 to plus decimal 80. That moves us down 1 line of the screen, and then we repeat for the remaining lines, selecting the new VRAM address for the start of the next line after each write. And then finally we've just got an infinite loop here. Now you saw before we had loaded our Chibico position, but if we change these values here, if I change this to 40 and 40, well, now our Chibico will be much further down the screen. There we go, our Chibico's all the way over here now, so we can move our sprite around the screen as we require just by changing the VRAM address that we write to. As I say, this is the easiest way of doing things. It's not the fastest. Another option is to get the sub CPU to do the work for us, but that's a little bit tricky because we have to negotiate with it and send data to it. The fastest option is actually to remap the VRAM screen so that it's part of the addressable memory to our main CPU, and then we can just transfer data from CPU RAM to CPU RAM without using the wrap device at all. We're going to do that on a later lesson, but it's more complicated. So today we're just doing the simple one. I'm sure I've scared enough of you already by trying to describe the layout of the memory, because it scared me enough, so I understand it will probably scare you. Anyway, that's all we're covering today. I think the UKNC is a fascinating machine, and I think it's an excellent way of, if you want to play around with PDP-11 and you want to see something a bit more tangible than a console, if you want something a bit more visual and you can play around with, I think it's really fun to see graphics on the screen, and you know, it allows you to try out different things and see a more visual result than your command line console. So I'd certainly recommend you take a look at it. And the multi-CPU element of it is quite fascinating, because there's relatively few systems that have multiple CPUs in these old 8-bit days, and the UKNC has done a very good job of it. I mean, it's very flexible with the ability to remap the VRAM in the way that it has, and I think it's faster than the FM7 as well. The FM7 tended to be a little bit sluggish. So as I say, I'd certainly recommend it as one to consider. Anyway, I hope you've liked this. If you have, hit the like and subscribe. And we'll be coming back to the PDP-11 in a later tutorial. We'll be looking at 8 colours and then how to reconfigure the VRAM for more advanced things. Anyway, hope you've enjoyed this. Thanks for watching, and goodbye.